Welcome to another summary video for Diploma Program Physics. This time I'll talk about topic 5.3, which is electric cells. Hopefully all the knowledge you need is included in this one slide. Obviously I'm not going to apply it to many examples, but basically what is an electric cell? Well, it's a device which converts chemical energy into electrical energy, which we can use in our circuit. So in an ideal cell, firstly maybe let's just define the concept of electromotive force, epsilon, or EMF. It's basically defined as the work done in moving a charge across the terminals of a battery. So if we have charges, and if I was to move one from the positive to the negative, divide that by the number of charges, that would give me the electromotive force, which is actually the units are the same as voltage, so the units are volts. So to call it a force is rather misleading, but it's a measure of potential difference. And in an ideal battery, there we have no internal resistance, so we only have the EMF provided by the cell. But in any real batteries or real cells, we have what's called an internal resistance, little r, which is in ohms. And basically within the battery itself, some energy is used up because some energy is lost basically when electrons are having to pass through the materials of the battery. So if I was to measure the total potential across the terminals of the battery, then it would actually be equal to epsilon minus IR, because we've lost some energy already within the battery. In order to experimentally find the EMF and the internal resistance, I would connect up a circuit similar to this, where I would measure the potential difference across the terminals of the battery, and I would put externally a variable resistor in place, which means I can vary the current in the circuit. By varying the current and measuring the potential across the cells, because V equals epsilon minus IR, V is my Y variable in this case, and I is my X variable. So the Y-intercept, if I was to extrapolate back, would give me the EMF, and the gradient of the straight line graph will be equal to the negative of the internal resistance, little r. Now, if I was to connect a circuit or a cell in series with a resistor, if I have a low value of the resistor, I would get a high current. It would discharge very quickly, and I get a discharge characteristic like this, a very steep drop to a constant value of potential difference, and then suddenly a drop down to almost zero potential difference. However, if I was to have a lower current in the circuit, then the discharge characteristic would take much longer, because there would be fewer charges flowing per second, so the discharge time would be extended. Finally, you have to know about primary and secondary cells, whereby a secondary cell, or when we talk about secondary cells, we mean a rechargeable cell. So if I place a large or powerful primary cell in the top here in series with a secondary cell, but I've reversed the polarity of the secondary cell, current flows from, or in this case it's going to flow anti-clockwise, but it's going to flow into the positive cell terminal of this cell and charge it up. By the electrons will be converting electrical energy to chemical energy again inside the cell. And by using Kirchhoff's loop law, I can see that in this example I'll have plus 9 volts, negative 14I, and then negative 2 volts here because I'm using up energy in the secondary cell, means that I can find the current in the circuit to be 2 amps.